Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. This video today is going to look at C++. It's going to look at pointers, everyone's favorite activity. We're going to look at a couple examples here. We're going to go down to the excruciating detail so you can understand what's going on down under the hood when it comes to memory addresses and what's actually happening. And let's just start with it. So problem example 1 here. If we weren't using pointers, this would be a very, very simple problem from like chapter 2, just to get everything going. I'm going to ask the user, my input stage is I'm going to ask the user to enter a length and enter a width, just 2 integer values. And from that, we're going to use pointers, of course, but what we're trying to get across here is we're going to figure out the area and print that out. So length times width, very simple stuff once we get there. And then when it comes down to it, we're going to say, is the length greater than the width? Is the width greater than the length? Or are they the same? And if they're the same, you go, oh, it's a square. So again, the only true difference here is we're going to introduce the idea of pointers. And we're going to introduce the idea of all the memory addresses that go with that. So here I have an Excel spreadsheet already set up, and we're going to work with that. We're going to work together between the two here to make everything work and give you a good example of what's happening under the hood. So let's get started. Okay, so you can see right off the bat that length and width are individual, just normal variables from everything up, everything we've been doing up till this chapter, the pointers chapter. And so like when our program runs, the operating system gives us a block of memory, and inside that block of memory, pretty much any variable that you set up can be kind of placed anywhere. That's kind of why I kind of spread these across, because we're going to use 5 of these things: length, width, length pointer, width pointer, and area. I think that's all we're going to use here. Yep. So I just kind of spread them across because they could go anywhere. Because let me just show you right up front here. If I do something like this, I say print out the address of length and then print out the address of width. And then just give me an extra space here. Before I even print anything else out, this will not compile as is. So give me a second let me just fill this in. Just for now, just to make this a working copy. I forgot that this thing is something like that. So now I can actually run this, I think. Pretty sure. Oh, yep. Okay, and then it comes up. And you can see here that it prints out weird stuff. And again, this is hexadecimal code. This is base 16. This is just a different representation of a 32-bit integer. But at least because on our architecture, every memory address, our memory address scheme, at least with this version of Visual Studio, is 32-bit. We haven't moved up into 64-bit mode just yet here. This is just running 32-bit. So this is saying that the memory address of where length is in memory is this guy. So let me just steal that. Let me put that right there. And then let me steal this guy and put that here. So the address, to us, on our end, the programmer side, we're using the variable name length. But when it comes down to it, our code, the program is actually, when I say length, it's actually pretty much accessing this memory address. And when I say, hello, there we go. When I say width, the computer is actually using this memory address. So it's just a way for us to communicate with the computer and say, I want some memory, use this specific memory for this and use this specific memory for that. And one interesting note here is we're just going to leave this as is, but if I run this program a second time, you will see that the memory addresses are different. And you're almost 100% guaranteed this, and that's because every time we run our program, the operating system gives us a different block of memory. And it would make sense that if they're giving us a different block of memory, then these variables are going to be placed in different places in our RAM. So when I go ahead, okay, so just saying that now. So when I can get rid of this now that you have that understanding that these things are like that. And just for the sake of right now, I'm going to say the area. I'm just going to make up a number, zeros, and just be kind of consistent. 0, 0, A, F, F, B, and I'll just say 3. And I'll say 8. I'll just say, okay, so it's the same deal. Area is just an integer variable, and it gets some memory address as well. Okay, we'll deal with these guys in a minute. Let's just kind of get to this. So what happens here when it says enter the length of the rectangle, and I input a value, basically it says, okay, cool, go to the memory address where length is and put in a 10. Let's just say I input 10. Okay. And let me steal these guys here and just let me center this. Make me feel better about life. There we go. Okay, so 10 is the length. So don't get confused between the address and the value stored at that address, because that's going to come into play when we deal with the pointers. And if I say something about the width, and I say, okay, I'm going to put in 15, it goes to us where width is, but it goes to that memory address in our RAM and puts the value 15 into the 4 bytes that are stored there for our integer value. Okay, so now we're going to deal with this pointer part of this, because again, it's real easy if we just had length times width to figure out the area, but the whole point is to get used to the idea of pointers. So this is saying integer pointer length pointer, and I already have this listed over here. And again, every variable, in this case it's a pointer, but it's still a variable under the hood. And a pointer, any pointer, the only thing that gets stored in the actual, in that memory location is another memory location. But, this is the tricky part here, is that since these are variables, they still have, and I'm just going to make this simple here. I'm just, oops, A, F, C. I'm trying to make this simple anyway. There we go, 1, 2, 3, 4, 5, 6, 7, 8. They still get memory addresses, and I'm just, oops, and I'm going to just, something like that. They get different memory addresses, and again, every time like anything else, but again, to us, it's called length pointer, but to the computer, it's called this memory address. This is called width pointer, and to the computer, it's called this memory address. And because it has this little star in front of it, this is telling us that this variable is storing a pointer that's a memory address to another integer value. And right now, it's set to null. 0. Don't worry about area just yet. This is still uninitialized. So I can leave that like that. But it's there. It's being used as part of my program. Okay, but now it says, okay, change the code to make length pointer point to length and hold its address. Because I can't just say int pointer length pointer equals 3. That's just not allowed. There we go. A value of type int cannot be used to initialize type int pointer. Okay, fair enough. So what I can say, and can I just say this here? Int pointer length pointer equals length. I can't do that because this is an int. You get the same error. A value of type int cannot be used to initialize type int pointer. And that's because this is, to the computer, this is an integer and this is an int pointer. So to go from, basically to go from length, which is storing the 10, to the memory address of length, I use that little ampersand like I did before. So now this is okay, because this is saying, okay, length right here, length, tell me the address of, so tell me what the computer thinks you are when it comes to where you are in memory. And it gives me this value right here. And then it says, okay, take that value and put it into here. So that's actually what's being stored here at length pointer. It's a memory address to a different place in memory where the actual value is stored. So now we have 2 ways to access the same data. One basically by value and one by pointer, by reference, if you want to think of it, by not technically the same reference and pointer, but it's close enough for the discussion right here in the moment. So now the same thing goes down here. I have to say basically, ampersand width. Because this is saying, okay, this is a pointer, and this is going to point to whatever memory address this guy is. Because now I have 2 ways to access the data here. I can access it directly through width, or I can access it indirectly through width pointer. And that's what we're trying to get across here. And again, we would never do this in the real world. This is just to get the understanding of what we're what we're doing with how pointers work, how memory addresses work, and so forth. Okay, so now the input stage is complete, because we have our length value, we have our width value, And I guess depending on how you look at it, this could be technically calculation or this input. We have all, anyway, no matter how you look at it, we have all the givens. We have all the information stored how we want it. We have 2 values stored from the user here, and then we have 2 pointers to that memory over here. Okay, so again, I was saying, change this code. I could very easily just say length times width, something like this. And it would, and so that's pretty simple. Again, this is just using length and width like we always have. And just to 100% prove it, 10 times 15 is 150, of course. And so there it is. The area is 150. Don't mind the extra stuff here since we haven't fixed that up yet. But the area is 150. Exactly. But what if I want to use, instead of length and width, I want to use length pointer and width pointer, because that's the whole point. That's the whole point here. So again, I can't just say something like this. And you can see this goes wrong automatically here. This expression must have arithmetic or unscoped enum type. Oh my goodness, right? What the hell does that mean? But just what this is saying, though, that we know this is a pointer. We can't do pointer arithmetic like this, where we say, oh, hey, pointer, multiply by this. Because, again, under the hood, length pointer is just this value, which is, it's just garbage, because to us, right, it's because it's not really a value. It's not holding a 10. This isn't holding a 15. They're like, well, how would you expect to get anything that's halfway reasonable for a response to this? So that's why the compiler says basically, nah, you're trying to do pointer arithmetic and you're trying to do pointer multiplication, which makes absolutely no sense whatsoever. So what we have to do, instead of using length pointer, which points to this memory location, we want to get, or to get to this value stored in here, we want to get the 10. And so there's one extra step. It's direct when we use length, but it's indirect when we use length pointer. So what we're trying to say here is, okay, I know I have a pointer, so it's storing a memory location. How about you go to that memory location and then get me the value stored there? That's the idea, right? That's what we would want to be able to do, is say, hey, length pointer, take, go to wherever you're pointing to, whatever memory address you're pointing to, get me that value, and then bring it back so I can use it. And to do that, I know it gets a little complicated because there's 3 different ways to use this star here. We put a star in front of length pointer. So again, here's 3 different ways, right? The first one is obviously multiplication. We can use star for multiplication. We use star to set up a pointer. And then we use a star to what we call dereference the pointer. So that's doing exactly what I was saying a minute ago. Hey, length pointer, I know you're storing an address. Why don't you go to that address, and then get me the value stored at that address and return that. And then this will get me the 10 out of the whole deal. And then, of course, it's the same. I'm going to do the same thing here. And it gets complicated with star, right? So you might want to use parentheses or something like that just to kind of differentiate. Because it can get complicated. You don't normally well, I don't know, whatever. You do what you need to do, right? But C++ is famous for having all these crazy symbols all over the place, right? So now I'll get the same result if I put 10 and 15 in. And the area is 150, just like before. And now we can do the rest, and we will. But just one last thing to consider here is, again, since I can dereference, I can get data. This is us getting data. I can set it as well. So just saying, like, if I move this up, this is just, this isn't part of the assignment per se, but this is just to maybe kind of strengthen your understanding of what the heck is going on. So again, at this moment, when I put the 10 and the 15 in, previously we put the values directly into length and directly into width. But like I was saying, I can dereference. So I was showing you how to dereference on this end, right? Oh, length pointer, star length pointer. Sorry. And star width pointer. So now this is getting the data, and now this is storing the data. Because this is now saying, hey, length pointer, cool. Why don't you go to that memory location, and whatever the user put in, put that value in. So again, there's two different ways to access the data both ways, setting and getting. So you got to watch out for that, because there's only one data, the data is only being stored in one place. But I'm allowing two different ways to get to it. And because there's two different ways to get to it, it's this one data. If I change it, it affects both. So now again, just a third way to get to the same data, or second, or at least a second way. And now I get 150 again. So I'm never directly, you can see this, I'm never directly using length or width, but I'm still storing the data inside of there by using the dereferencing. So this is how you set the data. I know it looks weird because it's the same exact thing, right? But this is setting the data, putting the data inside of here, and then this is getting the data out using the dereferencing of the pointers. Okay, so just to finish up here now, since you know how to access the data, you could do it two ways, right? You could just say, okay, if the length, words start looking funny, right? If length is greater than, and so you can kind of combine them if you want to. I'm just showing off, right? But again, just to kind of show you that you can do things two different ways. If length is greater than star width pointer, because I could have said just width, if length is greater than width, but I just want to show you that I can access length this way, and I can access width this way, and it still gets me the data in the same way I want. This is going to get me the 10, this is going to get me the 15, and the same thing goes if I want to reverse this on the other end here. And if I say, okay, how about star length pointer if it's less than width, or star width pointer, or whatever, just to say. And then, instead of saying the width and the length are the same, how about you have a square there, fella? You have a square there, fella. Season 6 or 7, my God, what year is it? 27 years ago, Simpsons episode or something like that. Just so we can get across that, what's what here, because it's kind of hard to read this. So let's try it now. Let's try it the three different ways. I say, okay, the length of the rectangle is 10, the width is 15. Okay, the width is greater than the length, or the width is greater, longer. How about longer, right? The width is longer than the length. The area is fine. How about I switch it? 15 and 10. Oops, sorry, I gotta drag it over. The area is the same, and now the length is greater than the width. So it's all working out. And now, again, just to finish up, just to make sure, if I put 10 and 10, you have a square there, fella, because these are exactly identical. And if you made it this far, I totally get you, like, why the heck do we do these things? Why are we bothering? And I get that. I understand where you're coming from. And I was asking the same exact questions way back in the day when I was learning this stuff. But the reason why we're doing things this way and teaching you pointers now is when we get to chapter 15, and that's the inheritance and polymorphism chapter. We absolutely need to do this kind of stuff in order for inheritance and polymorphism to actually work. If we neglect pointers, then we can't do any of that extra cool stuff that we're going to teach you. And it applies across the board. Only when I was out in the real world and I was newing and using pointers everywhere and going, why the heck are we doing this, that it all finally clicked for me. And I'm trying, so if it didn't click for me till I was out in the world, maybe it won't click. I'm just trying to make sure that maybe it'll click for you maybe 2 or 3 years before you get out into the world. And you'll have a better understanding of things than when I did. So anyway, so this pretty much covers everything for the first example. And it covers everything, just a description of what the heck's going on under the hood. And, and then the area, of course, I'm sorry, I never described the whole area thing here. Just saying, I could do length times width, or I could do this. And this says, just to finish up, just to say, okay, go to length pointer, dereference it, and get me the value, 10. multiply it by going to with pointer and getting that value, so the 150 will go inside of there. Okay, so that's everything I wanted to cover with example 1. Now let's move on to a deeper example. Now we're going to do pointers with and creating the memory what we call dynamically at runtime instead of at compile time. All right, here's the second problem. It's in a way, it's kind of the same as the first. At least the second part is the character pointer here, the character array. This is basically, we're going to show you how we did things before the C++ string came along. So we're gonna old school it here. We're gonna climb up the walk up to school, walk up the hill to school both ways, coming back home and going to school here. This is old. This is clunky. It is what it is here. So the first part, what we're going to do is enter your last name with exactly 10 characters. If your name has less than 10 characters, please repeat the last letter. And if your name has more than 10 characters, just do the first 10, right? So just probably should be a little more clear about this. This is again, you can see how clunky this is because you're basically telling the user, I only have enough space set aside for you. Please don't ruin this for me. So we're going to start here. We got character name, and we're going to do this dynamically. So this is a little different here. And dynamic means at runtime. Everything we did previously was all figured out at compile time. All the memory addresses, where what we're pointing to, this or that, all the memory that we're using. The compiler knows exactly how much memory we need before the program starts. But now what we can also do is do things dynamically, and this is much more powerful because then as the program is running, the computer can allocate and deallocate as much memory as it needs as it goes. And so the program can live a much nicer, cleaner life. There's a lot more responsibility that goes behind that. And again, that's why we push this off to later chapters, and with inheritance, polymorphism, all the object-oriented programming and everything else, everything just kind of just comes and just joins into this big ball. And maybe let's say hopefully one day when you get there, this idea won't be so bad for you. So to set everything up here, I say, okay, I want a character pointer, but now instead of setting it to a memory address or something like that, I can say, okay, give me, when the program's running, hey operating system, can you give me 10 bytes of storage? Because I can't do just char 10. I don't think I can. There we go. So it says type name not allowed, and so but I can new it up. So this is saying, okay, hey, and the memory is going to be put in a completely different place. What we were doing earlier, when I showed you that, when I had that Excel spreadsheet open, everything was basically in RAM, but it was all in the basic where the program sits. The program's memory. But when I call up new, what that does is there's a place of memory. It's still RAM. But it's not where my program is. It's the operating system is maintaining all the other memory. So this is what we call the heap. When I go, hey, operating system, can you give me more memory than what I was given when the program started? And as long as there's memory, the operating system usually goes, sure, here you go. And so now this gives me 10 bytes of storage. And if I run this, let me put a breakpoint in here. Let me just see what. I'm actually curious, what is stored in here? You can see it's all garbage. Oh boy. There's nothing, so this is, oh my goodness, look at that. This is the memory address of what was given to me. And then this is the data that's stored there. And it's garbage, it's complete garbage. And that's because whatever is stored there is just whatever was randomly put into that memory location. So I can initialize, because we've talked about arrays and we've done all this stuff, I can just, if I want to, let me try this again. This better work. By putting those curly braces there, now you can see that now this was replaced with zeros. Every element, every character in this array a zero was put in here because I explicitly put this in here. This says initialize everything to 0, essentially. And you don't necessarily have to worry about this right now. But I just wanted to show you the difference between the two. this says, okay, don't initialize the memory you give me, and then the other one said, okay, initialize the memory that you give me. Okay, so now that we've set up the data structure, now we can use it as if we didn't dynamically allocate it. We can just use it as if it was a 10-character array. And so the tricky part here is, and again, we would never do this like this in the real world. This is just trying to find examples of pointers and addressing and things like that, just to kind of get the point across here. So again, remember that we're assuming that when the user puts in data, they're going to put in exactly 10 characters of data. So that because because of course the user is going to read that and go, oh yes, exactly, I'm going to put in exactly 10 characters of data. We're going to presume this. We're not going to do any checks to see if they screwed up or anything. We're just going to presume the happy situation here. And so this says fill in the code to read character by character, all 10 characters into this, excuse me, but without using a bracketed subscript. Because what we could do is something like this, where you say, okay, enter the name, and then I could say something, I could do something like this. And I have a breakpoint here just to show you, and let me run this. So what this will do is it will, if I put an A, B, C, D, E, F, G, oh my H, I is the 9th letter, so J is the 10th. And so there's 10 letters, and I go boom, enter. And what happens here, you could see that name, oh boy, here you go. A, B, C, D, E, F, G, H, I, J, and then there's garbage after it, right? And you're like, what the heck is going on? I mean, you just got to trust the system. You just got to trust the process here. And let me see what happens if let me just see what happens then if I do the same thing over here. Let me just make sure, because it didn't look like it would print out nicely. But let's see what happens. Put a breakpoint here instead. Let's run this. I'll put A, B, C, D equal to, A, B, C, D, E, F, G, all that stuff. A, B, C, D, E, F, G, H, I, J. Okay, so it does print out, even though it kind of looks weird in here. My mouse over. It's got extra garbage after the J. It's still doing its job, and it's printing out those 10 characters exactly. And of course, like I said, like in a real world situation, we're using C++. We're going to use the standard template library string class. But we're not doing it today. Okay, so now what do we do? How do we fix this? So just to kind of play with this kind of cool, I'm going to leave this alone because I do want to iterate 10 times through. But I want to do this without using the bracketed subscript. So what I can do here is I can say, give me a character pointer, and I'll call this current, and it'll be equal to name. And so this is actually allowed because name is a character pointer, and current will be a character pointer. So I can just, this time I can blindly just go, okay, you are equal to this. I don't have to worry about an address. I don't have to worry about a dereference. I don't have to worry about any of that nonsense because the data types are an exact match. I could just say character pointer current equals name. And the reason why I'm doing this, setting this up, is because I don't want to accidentally change what name is pointing to. Because if I do this, if I change the address, because this again, even though this is memory, we only can access it because this returns the memory address of where the operating system says, yep, this is where it's going to be stored. And it's not stored anywhere else in our program. So if we lose that data, if we lose this, where this character pointer is actually pointing to, then all bets are off and we're probably going to crash our program. So I want to make sure that I don't change the original pointer, but I do want to go through and iterate through and play around with this thing. So I'm saying, okay, cool. But I can play with current instead of name. And so what I can do here is say, okay, instead of name and square bracket position, and we've discussed this in the previously 10 minutes ago or however long, I could say, oh, look at that. I can take current, the pointer to current, where in memory, and I can go ahead and say dereference that and put the data in there. Put one character into that right there. And this isn't going to work right. But it's almost there. If your name, blah, 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 A, B, C, D, E, F, G, H, I, J. And now the question is, what is going to print? I think it's going to say hi, J. What is it going to do? Well, where is it? There it is. Hi, J. And then there's just all sorts of nonsense after it. And again, don't mind the extra nonsense just yet, but you can see it's hi, J. And the reason for that is because this current is pointing to the first character in the array, the first element. And this is going around and around and around, and it's just basically saying, I'm doing this 10 times, getting the character from the, from the input, but I'm putting it at the first element, at the first element, at the first element. So the only thing that's truly printing is the J. And the reason why it's printing extra nonsense is because there is no null terminating character, so we're lucky it only printed this and didn't crash, to be honest with you. So how do I fix this? I have to move the pointer. Say move over one space. So get one character from the input, put it into the array at the current location, and then move over one. Get the data, put it into the array, move over one. So now if I do this, I should be in the right position. A, B, C, D, E, F, G, H, I, J. Oh, goodness gracious. And now it prints everything out like it did before. All 10 characters exactly. And again, this is a contrived example, but it gets the point across. And it's the same thing will now go here. Because like what would happen? Here, let me see. Name put, let me just say this. I could do this. I can go plus plus name. I can, can't I? I think I can. And I can. And this is the weird part of all the way pointers work. And what will print out now? Pointers are fun when you clicks. So what do I do? A, B, C, D, E, F, G, H, I, J. Boom, done. What did it print? It printed B, C, D, E, F, G, H, I, J squared. And that's what I was describing earlier. I didn't want to modify name, but I did. I did it purposely, but you can do it accidentally. But that means now, anytime I want to print name out, oops, it thinks that the second element is the first element because that's what I'm pointing to instead of where I thought I was. So that's why I used current the entire time here. And so by putting this back here and doing the same kind of thing here and saying current equals name, and then stealing this guy, and doing a C out instead of a C in. And then what I can do, I can actually put a plus plus here. Isn't it weird? You can put it on one line if you want, and this is where things start getting weird, right? So this, what is the order of operations? This guy works out first. So it'll take the current location, which is the first element, print out the value stored there, which is the capital A, and then move current over one. So you can do it in one line of code if you truly want to. Okay, whoops, I don't know what I hit. I don't know what I did. There we go. So now coming back here, A, B, C, D, E, F, G, H, I, J. And then I'm going to stop this right now. Stop this nonsense. And now you can see there's I, A, B, C, D, E, F, G, H, I, J. And then that's where the cursor is. So just to be on the safe side, I can also put an exclamation point and an end line. So if you understand everything I was just describing, I'm pretty sure I was correct in my description. Pretty sure. Pretty confident. Then you're on a good track then. A, B, C, D, E, F, G, H, I, J. And there we go. There's no extra characters, no lesser characters. And again, I'm curious, what does happen if I just put Brad in with nothing else? Interesting. It's still waiting. It's still waiting for 6 more characters. So there you go. Hi, Brad Burr. Because, again, we told it that we're going to process exactly 10 characters. And if we wanted to change this around, we would have to rewrite all of our code to search for a null terminating character and all sorts of nonsense. And it gets a little tricky. Because you can even see here, the null terminating character is automatic. Oh, maybe I can't see. Come on, guys. There we go. You can see it says, even for that, it says const char 2. Even for one character, because the exclamation point is the first character. And then what it doesn't show is that there's a 0, a literal 0 as the second character. And that's how C pure C determines the end of a character. The null terminating character is a 0. All right, so that covers everything for this first part when it comes to that. So now let's move on to part 2 and call it a day. So pretty much the difference between like this part 2 here is is just dynamically allocating the memory instead of pulling and saying, oh, I already have a variable and then I'm creating a pointer to that variable. Technically, that variable does not exist until I dynamically allocate it. I have a pointer to it, but it doesn't exist until I say, hey, operating system, give me a variable that I didn't know I was going to need at compile time. So like this, fill in the code, new int. And you don't have to, you needed the square brackets in order to do set up an array, and it's weird, right? Because this is character pointer. There's no real difference between when you new up memory, if you're going to new up a variable versus an array. This is just saying, okay, set up 10 characters for me. This is basically saying set up one element of int, but this is still 4 bytes of storage. So new int, and you do the same thing here. I think, yep, int pointer, int pointer, int pointer, new int, new int, new int. And if you want to initialize it, you can put a number in parentheses. Let me make sure you put that in parentheses if you want to initialize it. Or I think you can use the curly braces. You can use the curly braces, but you don't. If you do this is setting up an array. So you got to watch out. So I don't need to initialize everything because the user is going to put those values in as they input. Okay, int pointer 1 equals new int. Int pointer 2 equals new int. Int pointer 3 equals new int. Okay, enter the 3 values, and we're only working with the pointers. So I can say, okay, and like I described before, I can't just do this. Because again, as pointers, there's no way to input data as a pointer, because there's no way to know. So that's where the dereference comes from. You can see the arrow move. Oops, you can see the error move over as I'm fixing this thing up. So this is saying, okay, take the integer from the input, go to the pointer, and go to that memory that it's pointing to, and put that value inside of that memory location. And it works it over 3 separate times. And I have to do things this way. Oh, let me just, who cares about, oops. I'll comment that out in a second here. Okay, so enter 3 integer values separated by blanks. And the blank is always the delimiting character unless you change it up. So 34, 22, and 17. So my 3 numbers are, and you can see, 1, because it's a pointer, it tells me the memory address, but it also tells me what's stored there. 34. 2. The 22 is stored there. 3. The 17 is stored there. So you can see, and again, just to print out the 3 numbers, and you might think, oh, this is cool. Let me just get rid of this end line here. What I can do is I can print out 1, and I'll print a space, and then I'll print 2. You think you're so suave, and you're coming, for me too, you're coming off Python. You guys ever code in Python? You get that Python high, because it's like, Python is a fun language to code in, because it does so much in so little amount of code most times. You're like, this is so awesome. And then you come back to C++, and you're like, oh my god, how much work do I have to do what? So like in this case, oh, I forgot to let me just comment this out. Boom, just so. This is annoying. Okay. Oh, stars. Yeah, usually do it the other way around. Okay, let me start over. There we go. Enter 3 values separated by blanks. 1, 2, 3. And you can see now it prints the 3 numbers are. And again, coming back, this will compile, but again, like I was saying, what is actually being stored by a pointer is a memory address. So there's no reason why you can't tell it to print out 1, 2, or 3. It's just that it's printing out what is stored in that variable, and it's just this memory address to a whole different place in memory where the data is actually stored. So just like I did a minute ago, this was how I set the data, and I used the star to dereference on the other end to be able to get the data as well. And so to print out everything like I was expecting, of course, enter my 1, my 2, my 3, and now you can see now it's printing things out because it's saying, hey, go to wherever you're pointing to and get me that value, and then print that out. I say it's indirection. It's an extra level of indirection to get to the true data. And again, this plays a big role when you start working with dynamic or with polymorphism, inheritance, and this all your objects have to be newed up and dynamically allocated in order to use all the fancy functionality. Okay, so now the last step here is pretty simple. Fill in the code to calculate the sum, and then it's just *1 plus *2 plus *3. And if you just did 1 plus 2 plus 3, I think can you do this? I don't know. Let's see. Can you do this? No. It says fill in code to allocate. No. Expression must have integral or unscoped type, because it won't let you take a pointer and add another pointer to it, because it just doesn't make any sense. Because what would that address mean? It would just be garbage. The program would halt immediately because you're trying to access memory that you're not allowed to access. So now in this case, it should of course print out the 6. 1, 2, 3, and there it is. 1 plus 2 plus 3 is 6. And that is all there is to it. And then at this point you go, I'm done. But what about this? This is a big one. And this was a huge one. Like when I worked in the casino industry, this was the worst. And nobody told me this was coming. This bug, we call them PIDs. We didn't know this bug was coming. And then when it would come, you're like, what the hell am I supposed to do about this? The bug report would come in and it would say, hey, Brad, for the game that you're making, the game crashes. and how do I recreate this? And it would say, let the game run for like 52 days. And I'm not exaggerating. Like, let the game run for they would leave it on for 52 days, and then the game would crash. And you'd be like, okay. I get what you're telling me. This is absolutely ridiculous. How am I supposed to be responsible to find where that problem is? But what you knew was happening was, when I knew up memory, I'm talking to the operating system. Again, well, like we were saying, when the compiler does its job, and we call it statically, when the compiler is doing its job, when you don't dynamically allocate any memory, it knows exactly how much memory it needs to do its job. So when the program comes and the program goes, when the program starts and program ends, you end up with a net zero memory, because the memory comes 100 bytes or whatever, and then when the program goes, it gives back that 100 bytes. But here, when you knew this up, it's completely different. You're telling the operating system, hey, I'm now responsible for this data and for this memory. I'll tell you when I'm done with it. And if you don't tell the operating system that you're done with it, then it just chunks up. And the easiest way to show this is something like this. Is if I just say for, or while true, just boom, boom, just forever, new, and just give me a new, I'll use a double to make it a little faster. It'll be twice as fast. Just keep giving me new data. And let's see. Okay, program's running. I forget how long this takes. How much memory do I have? Blah, 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 yada, yada, yada. But this is saying, oh, hey, new. And then the operating system is just obliging, okay. And eventually, I said eventually, there it is. Bad Alec, because I've run out of memory. I have what they say, if I haven't said it before, it's called a memory leak. That I have just been giving, hey, gimme, and I'm never giving anything back. And eventually the program goes, nah, I don't have any more to give you. You're done. And so this is the problem. I newed up memory. We newed up everything for whatever we got here. I can put this back in now. We've got name, which is a new. We have, and we have 1, 2, and 3. And now we have to go ahead and say, okay, operating system, you can have the memory back. And that's what, so for every new, you got to have a delete when you're done with it. And usually, when you do this, you usually replace it with null pointer, not maybe at the end of your program, but just because if you don't do that, you have what is called a dangling pointer. Because what happens is the delete doesn't actually change the value that is stored inside of 1, but it tells the operating system that the memory that was stored at that memory location can be given back to the operating system. So what happens in this case? I delete 1, and then I try to print out the value stored there. Oh. And you can see a crash here, read access violation, because I'm trying to access memory that the operating system no longer is no longer giving to me, because I gave it back. And now immediately I want, hey, can I have that? And he's like, nope, you told me you were done. And the program crashes. So I have to do this, delete 1, delete 2, delete 3. And again, you're never going to necessarily notice this in a program, like especially if you're just, you're deleting it at the end, so you have to watch out. But this absolutely matters for large systems as you make larger and larger programs and you new things. For every new, at some point you need a delete. And we'll go, and it's an advanced C++ class, we'll give you more details on that. And then the final thing is you just got to watch out. If you new up just a variable like here, yep, that's fine. But if you new up something like this, an array, you have to use the special, and you just got to learn it. You have to use the special delete case, delete square brackets, and the operating system knows that it's going to have to give back 10 bytes. And so if you forget and you do this, this will work. I don't even know. Do you get a warning? Let me see. Do you even get a warning? See if I can. Let me rebuild one more time. Nope, you don't even get a warning, but you still have a memory leak. Oh, maybe it's warning here. Let's see. Name is allocated. See, there you go. Look at what a world. 2022 almost here. Oh, finally. So it's basically saying, are you sure you want to do this? Everything else is fine, of course, but it says, oh, you allocated name, you newed it up as an array. Are you sure you want to delete with just this boring old delete? I wish it would tell you the solution, but then this will get rid of that. And now you don't have... Come on. Hold on, let's rebuild. IntelliSense maybe behind? What is going on? Well, I think IntelliSense is behind here. Oh, there it goes. So now, by doing all of this way, delete variable, delete variable, delete variable, delete array, now I can guarantee you that there's no memory leak. And again, if you want to, you can just set this to null pointer. So you won't get an error. And null pointer is just a fancy 0. And every pointer of any type can be set to null pointer. And null pointer opens its own can of worms. Don't get me wrong, for those of you who are like, what are you talking about? But again, that's for another day. This video is already quite long, 40 minutes or so, maybe even more. But pointers, it's important to iterate and reiterate the points of pointers. Like, what's the big deal here? Why are we doing this kind of stuff? Okay, so that covers everything for this assignment. So I hope you enjoyed and hope you learned quite a bit about memory addresses and how we access things as opposed to normal variables. And again, we'll see this again in a couple weeks, week 13. All right, so if I have any questions, if I misspoke, or if you think I misspoke, especially with this, it's very possible I was the same way. Like, it seems to make sense, and then you say something exactly not right. So just let me know. swardb@cod.edu is a great way to get a hold of me, or you can comment below on the YouTubes, and I'll get back to you as soon as. Okay, so for those of you in my class, next item up for business is the whatchamacallit here is the exam, and then we move into structures, and then we move from structures into object-oriented programming. We are 1 month-ish away from the end of the term, and that's where we end up with, and we cover everything we cover when it comes to object-oriented programming. I cover at least, again, in advanced C++. So you get to see it twice, so it's not so scary, hopefully, the second time around when we get to implement and start using pointers and all sorts of stuff, like how do we create data structures like vectors and lists and sets and maps. All right, I'm going to stop blabbing. Have a great day, everybody. Have a great weekend, but have a great day, and hope to see you in another video. Take care. See you then.